Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. Welcome everybody binge watching us before the exam. So we are going to continue today on database design theory. I will really take the time to explain because it's complex, it's formal. So I'll make sure also to answer your questions and make sure that you have an intuition for all the concepts that we introduce. Remember that the goal of this is to design good schemas. This is why we are doing database design theory, because we want to avoid anomalies, right? So for the context of this lecture, we are working with sets of maps. You know that we can also support bags and lists, but we just assume a set semantics of the relational algebra. And you remember we have a set of maps and we fulfill relational integrity, we fulfill domain integrity, and we fulfill atomic integrity, right? So these are three examples of constraints that you can put on a set of maps. And in fact, what we are doing right now in database design theory is just that we are throwing in more constraints, right? Functional dependencies can be seen as constraints on a table, right? Super key can be seen as a constraint, and so on, right? So we are just throwing in more constraints. And there are also all the constraints you saw in SQL, right? Constraining not to be null, constraining to be unique, and so on and so on. All right, so this is what you already know. We've spent so much time on this that by now you know the definition of a table. However, one of these three got a promotion, and that's the third one, the atomic integrity, because in fact, it's also called the first normal form. That's the same name as the third one, atomic integrity. Another name of it is the first normal form. And really what it says is that the table is flat because you don't have any nested structures. That's what the atomic integrity, also known as first normal form, is saying. And as you might have guessed, since there is a first normal form, there is a second normal form, a third normal form, a fourth normal form, a fifth normal form, a sixth normal form. We will not cover all of them. We actually will focus on just one of them that is mysteriously known as the 3.5th normal form. And I have no idea why. It's just squeezed in between the third and the fourth. But this is the idea, that everything starts with the first normal form. And I've shown you last week, if a table is not in the first normal form, because it has nested tables, you can force it into the first normal form by introducing redundancies and duplicating some values, right? So that's what we saw last week. Typically, every one of these normal forms comes together with an algorithm to convert a table or a database of tables that is not in this normal form, to convert it into something that is in a normal form, right? So it's like how to fix the database schemas to obtain the normal forms. All right, but that we'll see later. Come back to the other normal forms. The first one just means no nestedness. Then we saw the idea, which is important because there is a tricky part about this, is that when you design, when you talk about functional dependencies, super keys, candidate keys, and so on, it's common to do it on a simple example, like you take a table and then you look at the functional dependencies and super keys and so on. But the thing is, in real life, you don't have just one table, you have a table that evolves over time. And it's important to keep that in mind, right? That when you talk about functional dependencies, super keys, and so on, you don't mean them just for one table, you really mean it for all of the possible tables that you accept in your database. And through time, I mean, if you're a large web store shipping billions of products, then you can imagine the high number of tables that you can have in there. But when you have these functional dependencies and super keys, they are here kind of to constrain the sort of structures that you have in your tables. Okay, so this't what we call a table universe, which is just a set of tables that share common constraints, right? Now, visually, that we saw last week as well, the idea of a functional dependency is that, in that case, AB functionally determines DE. It means that whenever you have tuples that match on A and B, the ones on the left, then they must also match for the ones on the right. So in that example, I showed you two places in here. All of the tuples that have foo and bar, that, for example, these two, must also have the same values there, in that case, true one. Here you have other tuples like that match on A and B as well, just in a different way. They must also match there. Then we have these functional dependencies, right? In other words, D and E are functions of A and B. You can build a mathematical function that associates foo bar to true and one, and that associates bar foobar to false and one. Here, it's broken because you cannot build a function like that, because bar foobar, what do you map it to? It disagrees here. So you can no longer build that mathematical function from the values in A and B to the values in D and E, right? So in that case, it's broken. It is not true that all tuples that match on A and B also match on D and E. We have a counterexample here, and that breaks the functional dependency. That we saw last week. So for whom is it clear, the functional dependencies? All right. And remember that an alternate way of seeing this is with a little game, that we have a table that both you and I see, and I'm secretly picking a tuple in that table. I don't tell you which one. And then I tell you, okay, the tuple that I picked has A equals bar and B equals foo bar, right? And then I ask you to guess, what do you think? It's hidden. I'm not showing you the tuple that I have, but what do you think the values of D and E are? Well, in that case, you're able to answer that it's surely false and one. You don't know which tuple I have, but because of the functional dependency, since I gave you A and B, you can give me D and E with certainty. Here you can't. Could be false one, could be true one. You don't know because the functional dependency doesn't exist here, right? So you can just think of it of that little game that you play. I'm giving you A and B, and you must tell me D and E. Now, let's play with this table right here. I actually, on purpose, picked that example to follow up on a discussion we ended up with last time. Let's start with functional dependencies. Can anybody give me functional dependencies here? Just throw in a few examples. Also on Zoom, you can write in the chat. Do you see any functional dependencies? Yes, go ahead. Yes, absolutely. Car ID functionally determines canton, number, holder, and age, right? This is true. What does it mean? Because it determines all of them. So what does it mean about car ID? It is a, anybody knows when it determines everything? It could be a primary key. In that case, it is a primary key. It's not always true. You could have also, for example, it is also true that car ID and number together determine everything, right? In that case, it's not a primary key, but what is it still? No, not candidate key. The other one? Super key, exactly. It's a super key. And this is great because that's an opportunity to now get into the details of what they all mean. Super key, candidate key, primary key. I'm just going to make sure that, that this is clear. So indeed, whenever you have a set of attributes that functionally determines everything, it's a super key, plain and simple. Now, what is a candidate key? It's a super key, but it's a super key so that you cannot remove anything, right? So you see that car ID is a super key, car ID and number is also a super key, but do you see that if I take car ID and number, you can remove things, you can remove number, right? And then it's still a super key. That's the reason why it's not a candidate key, right? It's basically too large, yeah? Yes, absolutely. Car ID is a super key and it's also a candidate key, right? Oh, you meant car ID. Yeah, then you're correct, absolutely. Car ID is a candidate key and a primary key and a super key. Yeah, absolutely. What I meant is car ID plus number is not a candidate key. That you agree with me? Awesome, yeah. So car ID plus number is not a candidate key because you can remove number. As soon as you can remove something from a super key and it's still a super key, then you don't have a candidate key. For a candidate key, you must not be able to remove anything. It has to be minimal, right? So car ID is a super key and a candidate key. And can somebody give me another candidate key in there? Who agrees that canton plus number is a super key? Everybody, right? Who sees that you cannot remove canton from here because number is not a super key, right? You have 1,000 appearing 3 times, right? So you cannot remove canton from that. Can you remove number? Also not, right? Because canton, you have 3 times the H. 2 times Neuchâtel, 2 times Uri, and so on, right? So you can neither remove content, nor can you remove number. Thus, content plus number is not only a super key, it's also a candidate key, right? Who agrees? Okay, that's because you cannot remove anything. And now, and that brings us back to the discussion that we ended up with last time, is that you see that I have 2 candidate keys here. I have car ID, which has 1 attribute, and I have content plus number, which has 2 attributes, right? And the point of confusion last time is that it's entirely possible to have a candidate key with 1 attribute and a candidate key with 2 attributes. That's totally fine. Because what is meant with minimal is only that you cannot remove attributes. What is meant is not that it has the minimum number of attributes. That's not what it means, right? So now I have these 2 candidate keys, car ID and content plus number. And what happens is that because I have these several candidate keys, I, as the designer of the database, can promote one of these as the chosen primary key, but it's my choice, right? And so you're absolutely correct when you said earlier that car ID is a primary key, in that sense that you could decide that it's a primary key. And you might argue with several reasons why you prefer the car ID rather than the canton number. For example, that in Switzerland, you can actually remove license plates and put them on our car, right? But these are real world arguments, right? You have a question? Number plus holder, let's look at it. It might be 1. Alan Turing, 1,000, yes. So the 1,000 you can disambiguate. Then you can, yeah, I think you're correct. So number plus holder is a super key. No, it's not. You have a counterexample? Oh, yes, absolutely. So that's your counterexample, indeed. Do you see it? So you have now twice the same. I think that's because I thought of it when I designed the slides and I copied it on purpose to try to avoid that. Yeah. All right. So great. And you agree with this, right? That it's okay, awesome. But it could have been, and the reason it could have been is because of an accident, right? Because sometimes just it so happens that that you end up with additional super keys, even though it's not generally the case, right? So, for example, here, if you change the numbers and at some point it turns out that all the numbers are different, so you don't have twice the same number in different contents, then you could accidentally have number be a super key, right? If that happens. And then it means that for this table, where number is by accident a super key, content plus number would no longer be a candidate key, right? Because it's no longer minimal. And this is why it's tricky, and you have to be very careful with these accidental functional dependencies and these accidental super keys, right? So whenever you talk about candidate keys or primary keys, you have to be careful to always have the universe in mind and to not have any accidents like this, because as soon as you have them, you're going to end up with weird candidate keys, right? So make sure that it is by intention a super key. All right. Any other questions? Yes? Mm-hmm. The difference is that it's the chosen one. So the primary key is basically a candidate key, but you chose it to be the primary key. So that basically means that you wrote down your SQL query to create the table, and you decided to write primary key with the attributes you've chosen. And the fact that you decide that a candidate key is a primary key, as opposed to another one, triggers a whole thing of automatic things in SQL. Right? For example, when you have the foreign keys pointing to a table, it automatically points to the primary key and so on, right? So it gets a lot of additional benefits basically by making it a primary key, right? And what you also get when you have a primary key in SQL is that it's going to make it very fast to look up a record based on the value of the primary key. That's an additional benefit you get. Right? But we'll look at this in a few weeks. It's called an index, right? And it's extremely powerful. Okay. Any other questions? Okay. Let me ask you a test quiz just to check that you followed, and then I'll continue. So some of these statements are correct and some others are not correct. So try to pick the ones that are correct. The first statement is that we say that a functional dependency holds for a table universe when it holds for all tables in the table universe. The super key holds for a table universe if it holds for all tables in the table universe. A candidate key holds for a table universe when it holds for all tables in the table universe. A unique constraint, the ones we have in SQL, holds for a table universe when it holds for all tables in the table universe. At least one of these is false. And it's directly related to the discussion we've just had a few minutes ago. We seem to have an agreement here that you're converging to an agreement. And you still have a chance to change your minds. Okay. So you agree for functional dependency, super key, and unique constraints, but not for candidate key. Yeah. Okay. So let me close, but the answer will not surprise you normally because the majority is correct. And this is the result. So indeed, for functional dependencies and super keys, that's how you characterize that it holds on the table universe. It basically holds if it holds on every table of the table universe. So if you have a table universe with 1,000 tables and you have a super key for each one of these tables, then it's a super key for the universe and vice versa. If you have a functional dependency that holds for all 1,000 tables, then it holds for the universe and vice versa. A unique constraint, if you think of it, what is a unique constraint? It's basically saying that an attribute alone is a super key, right? That's kind of the same. If an attribute alone is a super key, it's the same as saying that it's unique, right? So in a way, now you can map this unique in SQL. When you write unique after an attribute, that's kind of saying that's a super key. And the candidate key, that is not true. Why is it not true? So basically, you could have a candidate key for a table universe because it is a minimal super key among the super keys of the universe, right? But you could have, by accident, a table in the universe where the candidate key is no longer a candidate key. It's no longer a minimal super key for that very table, right? Does that make sense? I can come back, if I go to the slide, show you a concrete example of that. Here. If I take back this example here, basically on my entire universe, Canton number is a super key, and it's also a candidate key because generally Canton alone is not a super key and number alone is not a super key, right? So if I look at my entire universe, Canton number is a candidate key. For most tables, actually, in the universe, that's going to be true. Now, you will have a few tables in that universe that by accident happen to have unique numbers. It's just because you have 1,000 in Zurich and you don't have any in any other canton. But that's just a coincidence. It just happens that at that point in time, you have unique numbers, even though it's not generally true. Do you see that now, when you have by accident number with unique values, then it means that by accident number is a super key. And so it means that by accident, canton plus number is no longer minimal because on that table by accident, you can remove content and get number as a super key. Who understands this? Right? But this is an accident, right? And that's the reason why you have to be very, 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 very careful. Whenever you speak about the candidate keys, make sure that you don't look at the super keys by accident, right? So what we do at the exam to try to not confuse you is that if we ask you to look at the candidate keys on a specific table, so based on the super keys of that table, we usually add a hint in the question saying, don't worry, there are no accidental super keys or blah, blah, blah. You can assume that the table we're giving you is a good representative of the entire universe, right? So this is what we do. Yes? What a table universe is? It's basically something when you design a schema, you reason on the tables that you want to accept in your schema, right? It's basically, as a thought experiment, all of the potential future tables that you would consider acceptable tables in your database, right? That's what it is. And the reason is that when you think about super keys and candidate keys and primary keys and these things, you reason about the future, right? You reason about in the coming 10 years, what do you want to enforce in your database? Imagine your Digitech and you have the references. You want a product ID to be a primary key, a super key, a candidate key of the universe, right? This is really because you're considering all of the possibilities in the future. That's where it comes from. But typically, when you work on paper, you will try to take representative tables with fake data that you just populate with random values, just in order to reason about these things, right? Does it make sense? All right. Any other questions before I continue? Okay. Who has the feeling now they're with me? They're following? Okay, we're going to take it slowly. It's formal, it's theoretical, so don't worry. And even I can make mistakes, you know, even after all these years, sometimes my head spins because of the complexity. And if I make mistakes, then just tell me and I will correct it. All right. And by the way, the fact that I'm also making mistakes means that it's also okay for you to make mistakes. It's okay for everybody to make mistakes. We're in a university, right? Okay. So that's the accidents and so on. All right. Yes, but not at the exam. Exactly. That is absolutely correct, right? However, at the exam, you might see that we made mistakes. That's possible, right? And then you have, at the end of the exam, you have a text box where you can tell us, like, oh, I think you made a mistake in that question and so on. And then we'll consider when we grade. And even after the exam, you have the exam review where you can also ask about a clarification for a question. And it happens. And then we can even fix the mistakes. We can make a request for a grade correction. It's rare usually because we really double check things, but it can happen, right? So even we can make mistakes at the exam. Okay, but we try not to, of course, because if we of course prefer if the exam doesn't have any mistakes. All right. Okay, now the definition of a prime attribute. Just not to stress you, this is a standalone slide that doesn't have consequences until very far away in the future. So it's not really important if it's hard to visualize. But basically, what I call a prime attribute is I look at all of my candidate keys that I can find. So the minimal super keys based on my table universe or a table that doesn't have accidents. And basically, all of the attributes that are in at least candidate key, I call them prime attributes because they are part of some candidate key, any candidate key. The other ones I call non-prime attributes. Now, in our case, at least by intended design, here, what would be the prime attributes? All of those that are in a candidate key. Car ID, canton, and number. Yeah, these are the three prime attributes because car ID is in the car ID candidate key and canton and number are in the canton and number candidate key, right? Holder and age, normally, if I made the table without accident, should not be in any candidate key, right? If they are, then it's an accident, right? Maybe you will discover offline that they are, but this would be an accident, right? So holder and age, they are not supposed to be part of any candidate key. In other terms, they are not part of any way to identify a record, right? If I tell you the holder of a car or the age, this is not something that identifies the car. All right. Good. So this is prime attributes. Here, there's another example where product is a prime attribute, price, category, stocks. So just to give you an intuition of a non-prime attribute, typically something like a quantity in the inventory or something like a price or something like the age of a car and so on, all of these are non-prime because you cannot identify a product with its quantity in an inventory, right? That semantically doesn't make much sense. But on the other hand, anything that kind of has ID in the name, like car ID or anything that is part of identifying something, that is a prime attribute. Okay. For whom is that clear? Okay. Good. Now, I'm moving over, and you can forget, at least temporarily, what a prime and non-prime attribute is for the purpose of this. We're going to be doing math, but it's going to be math in a very mechanical way, in fact. And you will see it looks complicated at first when I show you all of these. I will try to explain it as simply as possible. But the nice thing is that when we give you the actual exercises and ask you to do it, at least in previous years, then this is something that you can do relatively well, because this is really something that you learn to do mechanically, right? So we are going to look at functional dependencies from an axiomatic perspective. So imagine that I have some table universe. And I'm trying, so imagine that I'm going brute force, like I have my table universe and I have this supercomputer of the Hitchhiker's Guide to the Galaxy, and it will find all of the functional dependencies in my table universe. It might take 1,000,000 years, but I will get all of them. So imagine I have that. And now these are my functional dependencies. I have attributes A, B, C, D, E, and F. So I have 6 attributes. And I know that on that universe, I have a functional dependency from AB to C, one from AB to CDE, and one from A to DEF. In other words, C, the value in C is a function of A and B. The value in CDE is a function in A and B. The value in DE and F is a function of A, right? These are the functional dependencies. So what we are going to try to do now is, instead of trying to derive the functional dependencies from looking at the tables for tuples that match on the left if they match on the right, instead of that, we are trying to reason on a very high level, just looking at these formulas and see if we can derive some things or make some deducing reasoning, right? So the first thing that we can do, and it's actually something that is relatively mechanical and easy to do, you will see, is called the closure of a set of attributes. Don't run away, here it comes. So imagine that I have some set of attributes in my schema, A, B, C, D, E, F, let's say, but there's more attributes in my table. And I want to extend it with anything that depends on it, right? For example, I could have on the left some set of functional dependencies that I know apply. So I got them while designing my schema or magically by brute force on my table universe. But basically, imagine that I have this functional dependency, right? I know that A and B together functionally determine G. If you know the value of A and B, then you know the value of G. So what we are going to do in order to compute the closure of A, B, C, D, E, F is that we look for a functional dependency so that what's on the left is part of my set. A and B are definitely part of it, right? So you see what I'm looking for. A and B here on the left, they are in here, right? So what's going to happen is that when the left appears in here, I can extend with the right and add this G here, right? And I can do it for as long as I can, as long as I find new dependency and I keep adding and adding and adding and adding, and maybe I do it for a very long time and end up with 3 more like G, H, and I. Then what I have learned is that A, B, C, D, E, F, if I know the values of A, B, C, D, E, F, then I also know those of G, H, and I, right? And in that case, I can derive from that a functional dependency like this, A, B, C, D, E, F, functionally determines A, B, C, D, E, F, G, H, I. So that's kind of the mechanics. But now let me explain in a different way the same thing. So if I roll back, here's the question I'm asking myself. Imagine still this game. I'm playing with, I show you a relational table and I secretly pick a tuple in there. And I'm going to tell you, just looking at my secret tuple, the value of A, B, C, D, and F, right? I'm giving you the values of that tuple, but I'm not giving you the others. And the question I'm asking is, if I give you these values of A, B, C, D, E, and F, what other values, what other attributes can you tell me? Right? This is the question I'm asking. And the reasoning is as follows. I have this functional dependency telling me that if I know A and B, then I know the value of G. So do you agree that then if I give you A, B, C, D, E, F, you can tell me G, right? Because in A, B, C, D, E, F, there is in particular A and B. We know from the functional dependency that if you know the value of A and B, then you know the value of G. So it follows that if you know the value of A, B, C, D, E, and F, then you also know the value of G, right? Who agrees? That's the idea. So you can really, when you look at a functional dependency for the purpose of what we are going to do now, think of it, read it as, if I know the value of A and B, then I know the value of G with this game where I pick a secret tuple. That's basically the idea. Then you can express it in terms of, I know that, and thus I know that, right? So basically, what we are going to do is add all we know, right? We know A and B, so we also know G. So I'm adding G to the list of the things that I know, right? I'm just accumulating all of the attributes that I would know, right? And so here I'm fast forwarding in the future, assuming that I also found additional functional dependencies that gave me H and I, right? And then with that reasoning, the conclusion that I came to is, if I give you the value of A, B, C, D, E, and F, if you know them, then you also know the value of G, H, and I. So all in all, you know A, B, C, D, E, F, G, H, and I. And since you know G, H, and I from A, B, C, D, E, F, what you have done basically is proven the existence of another functional dependency that I wrote on the left. You have proven that A, B, C, D, E, and F functionally determines E, B, C, D, E, and F, G, H, I. All right? Who is following? That's called the closure. So we'll compute on another example, and you will see, I'll even give you one as an exercise. You will see it's very mechanical, and you don't need to think too much when you do it. So here's on the left, all of the functional dependencies that I found for some table universe, right? So I have attributes A, B, C, D, E, F, G, H, I, J, K, and L. That's a lot of attributes, right? 12 of them. And I'm giving you functional dependencies. You know that A functionally determines C. You know that A and B together functionally determine C and D. You know that AC functionally determines B, and so on. In other words, if you know A, then you know C. If you know A and B, then you know C and D. If you know A and C, then you know B, and so on and so on, right? So that I'm giving to you, it's a given, an assumption, those on the left. And the question I'm asking is, if I consider the attributes A and B, so you know the value of A and B, can you compute everything you know, right? So that's the game we are playing, right? So can anybody try to give me, before we go through the comprehensive algorithm, if I know A and B, what else do I know? Can you give me a few attributes, just like looking at the dependencies that I would also know? Anybody wants to try? Yes? Yeah. Yes? Yes, yes. And L, absolutely. Yeah, so you did it completely. Congratulations. You basically solved the entire thing. And the way you did it is by looking on the left, and you added what's on the right whenever you could, you had what's on the left. That's exactly the idea of the algorithm. And somebody else on Zoom, I think, had the same idea. So this is great, right? Who agrees with this? Okay, many of you do. And for those who don't yet, I have the animation, but it's essentially what you've just been doing, right? I'm just repeating. So what we like to do as a first step is that we like to split to only have one attribute on the right. It's a common thing that we do. So if I have AB gives me C and D, this one right here, I'm replacing it with 2, right? This is the same. I'll come back to this equivalence. So I split this one in 2, like this. Now I do it for all of them. Next, I initialize here that if I know A and B, then I know A and B. So at that point, it's trivial, right? So AB determines AB. And then I go through the list. So that's probably what you did in your mind. So A functionally determines C, so I can add C in here, right? And then I gray it out, right? Now it's done. I have already used that one, so I can then forget about it. Then we go to the next one, but you see that I can immediately gray it out because I don't need it, right? I already know C anyway, right? I already have C in there, so that I don't care about. I already know that. The next one is AB. If I know A and B, then I know D, right? So AB functionally determines D. What it tells me is I have A and B here. They're already here, so I can add D, all right? And I gray it out. Then this one I don't care because B I already have in here, so I can gray it out. Now I have A and D, give me E, right? So I do have A, I do have D, so I fulfill all what's on the left, and then I can add E. Then I gray it out. FG give me H, can I use that? No, I can't, right? Because I don't have F or even G here. So that I cannot use, actually not yet, maybe in the future, but not yet. ABCD is useless. I already have D anyway. ABC determines I. This is useful. I don't have yet, so I can add it, right? Then I gray it out. I gives me J. I do have, so I add J. I gives me K. And C and J, I do have C and J here, so that gives me L. And that's it. And then I look again, there's only this one remaining and it's still useless, right? I still don't have F and G in here. So this, I cannot use it. That tells me that formally, the transitive closure of the set of attributes AB is A, B, C, D, E, I, J, K, L. And I note it like this with this little plus here, AB plus is all of that, right? And that's the mechanics for actually doing it. So it's really the idea of saying, if I know A and B, what is all I know? And all I know is A, B, C, D, E, I, J, K, L. Okay? And it means, in particular, did you see what I added at the bottom of the functional dependencies? Because I computed the transitive closure in this way of the set of attributes, the closure, then I proved that there is a new functional dependency that is also true, that is AB functionally determines A, B, C, D, E, I, J, K, L, right? Who could do it now on any other example? Okay. Do you want to do it on an example? I think I have a clicker question for you. Normally, if I prepared it well. Let me check. Yes, I do have it here. So let's do that, and then we'll have the break. So here's the thing. So the functional dependencies I'm giving in the question, right? A functionally determines B, B functionally determines CE, D functionally determines F, C functionally determines G, and H functionally determines F. And I want the closure of attribute set A, right? So if I know the value of A, what is everything else I know, right? So go ahead, try. I have a few 4 possibilities in there. One of them is the closure of the set of attributes. So you can either try to do it in your mind, actually, that's what you did earlier. So that's something you can do in your mind, or otherwise just on paper, trying to cross out the dependencies. You agree? Wow, this is very impressive, 100%. So I told you, right? It's mechanically, you can really do it, learn it very quickly. Okay. And it's really amazing because, you know, we are now doing pure math here. We just look at formulas and so on. We don't even draw tables anymore. I didn't draw any tables that have these functional dependencies. It's purely high-level reasoning, just based on the derivation of some of them, right? We have somebody who changed their mind. Maybe they're just playing. All right. You see why we don't have F in here, right? So F, we would need D or H, right? But we don't have D or H, so this is why we cannot add them, right? We cannot use the dependency D to F or H to F, right? And H, you can immediately see that it cannot be part of the solution because H is not on the right side of anything. So there is no way you could ever add it to the closure. All right? Okay, I think you deserve the break. So we'll take a break. Congratulations on that. And then we'll just continue to work on the high level with actions of functional dependency. So I'll see you at 15 past 11 for the continuation.